And we'll move on with Fritz Kalwa from Germany. Biological and physical clogging in infiltration wells, the effect of well diameter and gravel pack.
Yes, hello everybody. I'm going to present a little, so I'm going only into clogging. There's not much more that I will focus on. Can I? Here. So I think most of us know the concept of infiltration wells and of ISMAR wells. So there's mostly a screen that is either in confined or in unconfined aquifers. And when the water is infiltrating, then clogging can happen on those interface areas. So the costs for larger wells and or gravel packs, they're not always commensurate for the hydraulic effect only. So if you build a much bigger well, this is not always resulting in a much bigger infiltration rate. It doesn't always cover the costs that are necessary for building this bigger well. Sometimes it makes more sense to build several small wells to have the same effect. And small wells are much easier to construct and much cheaper, because the most important factors for drilling costs are, on the one hand, the geological setting. So hard rock is much more difficult to penetrate than unconsolidated sediments. Drilling depth is definitely important. The well diameter is one thing, because if you want to make a big hole, it's more expensive than creating a small hole. And a gravel pack is an additional procedure step that always comes with more costs. So I was asking myself, what about clogging? So what does clogging have an effect on well diameter and gravel pack? How do they actually affect the clogging? In general, I focused on two types of clogging. The most common clogging that is happening in infiltration wells is physical clogging, most probably, because suspended solids that are washed into the well, they will accumulate at the filter screen or anywhere else, and there's a linear increase in resistance to be expected that depends on the flow rate and turbidity. So the more suspended solids are washed in, the more the resistance will rise. With biological clogging, it's a little different, because this is mostly caused by biofilms that are created by microorganisms, by microbial activity inside the pores. And it's quite similar, so it's mostly dependent on nutrient supply, but also on temperature, or microbial activity in general. It's much harder to predict than what is actually happening with suspended solids. There's this figure by Pine that is quite, I guess most of the people here know it, that physical clogging is leading to a linear increase in resistance, and biological clogging mostly needs some kind of initiation phase to then rapidly increase, and depending on the food supply, it either reaches a certain maximum level or it increases even further if the food supply is abundant. One small thing that I want to stress here is that this is focusing on resistance. And when I'm talking now, I'm mostly focusing on hydraulic conductivity, which is the most common parameter that hydrogeologists know. So this is actually not much more than just dividing the resistance or the resistance by, or 1 divided by the resistance. Yes, so when it comes to clogging now, mostly this occurs in the first millimeters behind the infiltration wells. This doesn't only account for physical clogging, where it's obvious that most of the particles will accumulate at the screen or directly behind it, but also biofilms are mostly built up right next to the filter screen. So I asked myself, okay, so how is the well diameter affecting this interface area? And this is quite easy because it's first-class mathematics. You just calculate the surrounding area, you multiply it with the filter screen, and then you have your area. Furthermore, another factor is this gravel pack. How does this affect your interface area? Mostly it shifts this area away from the direct contact between the aquifer sediment and the filter screen, more into the sediment, and so everything will occur between the aquifer and the filter gravel. Something might also occur at this interface area, but depending on this is mostly negligible. That is what I expected, but we can discuss about this if you want. Yes. And why could this be interesting? So if you have physical clogging, it's quite obvious that most of the sediments, when they accumulate, so you increase your filter area, let's say we double it, that means we will also have twice as much time to clog it. It's like you have a sink, you wash your dishes, everything is washed out, and if your sink has a sieve that is twice the size of what you wash away from the dirty dishes, then you have twice as much time until it will be clogged. With biological clogging, it's much more like, I don't know, like when you catch a cold, a bigger nose doesn't give you more resistance against catching a cold. I think it becomes obvious that the topic has to be addressed in a different way. And so small diameter wells that are we focused on them a little more, especially my colleague Falk Hendel, who was also involved in this work. We wanted to assess a little bit, is it at all suitable for recharging turbid or nutrient-rich water at all? Because the first thing you hear when you say, hey, I want to use a small diameter well is, okay, so what about clogging? Then the other question is whether so if there's physical clogging that will affect our small diameter well, but if we only expect biological clogging to happen, so is it worth to invest more money to build a bigger borehole if we only expect this biological clogging? Perhaps the clogging might not need much longer to reduce our hydraulic conductivity here. And the other question would be whether if you build a big borehole, does it make sense to have this direct contact between the screen and the aquifer so that we have more space inside the well screen for pumps, for regeneration methods, whatever? Or is it necessary to build a gravel pack at an infiltration well only? So now we only talk about infiltration wells. For this, I created a setup. So this is mainly what you see here. It's not much more than 2 buckets put in each other. We have the aquifer sediment here. We have a drainage layer here, which is the second bucket. The water is infiltrating through the well. We can additionally build up a gravel pack here, and then the water is flowing from the well outside to the drainage. So they were all built up with the same sediment, all with medium sand, apart from 2 that I set up with the gravel that I use for the gravel layer, just to see what effects are happening inside the gravel. We had a constant flow rate into the well, constant water level at the drainage, so boundary conditions were very much fixed. And the clogging resulted in an increase of the hydraulic gradient. So clogging occurs here or here at the gravel pack, and this leads to an increase in the hydraulic gradient that we could observe. And with this increase in hydraulic gradient, we could again calculate the hydraulic conductivity of the sediment, or of this sediment layer between the well screen and the drainage layer, by just using Dupuy-Team. I think most of you know about Dupuy-Team, so I won't stress it much further here. Yes, in total I constructed 6 of those models, and I built them up with different setups. So for the biological clogging, we just had a closed circuit system of 100 liters of water. We added 30 milligrams of liter per day of DOC and some nitrogen also, 5 milligrams of liter per day. And so this was just pumped in a circuit, and we waited until the biofilm grew. For the physical clogging, we had water in the reservoir, we fed it with clay, and then we just pumped it up and we let it into the models. The water that was coming out here was just dumped. That's what they look like. Not very fancy, but they did their job. So you have to imagine that on those, there are still 3 meters of, I just dismantled them. So there were 3 meters of pipe on top of this to observe a hydraulic gradient of at least 3 meters, of up to 3 meters. Yes, so my first setup was mainly to test the diameter, the effect of the diameter. So I had 2 very small wells, 32 millimeters only, filter screen, outer diameter. 2 that were twice as big, so 63 millimeters, and 2 that had a gravel pack that was even bigger. So this was the first setup that I came up with. The second setup was mostly to test the effect of the gravel pack. So I had 2 of those bigger wells here again. Then I had the smaller wells equipped with the gravel pack, and then I had those 2 buckets equipped with gravel only, just to see how does it evolve in a gravel aquifer at all. So this is the clogging of the first setup. You see that the smallest ones. This is physical clogging, yes. So you see that the biggest one with the filter gravel, they actually didn't show much of an effect. The bigger ones without filter gravel, they just went down slowly, and the fastest, actually what you would expect for physical clogging. So this shows quite a big effect of this filter pack and the diameter also. When I check the biological clogging, I also see this effect kind of. Now again here the setup, but I see some kind of stronger effect here in this gravel pack units. So the hydraulic conductivity is decreasing a little bit more than at the physical clogging. If I see now the gravel pack only, that's what I mainly focus on here. You see the gravel aquifer, that is not really affected by physical clogging. You see that the smaller one without the gravel pack, it's quite heavily affected, and the one with the gravel pack is somehow not affected that much. So gravel pack increases the resistance against physical clogging, apparently. Now when we take a look at the biological clogging, we see that the gray one, this is a little confusing now, the gray one is the gravel aquifer. So the gravel aquifer is decreasing very much. Also, the gravel pack is decreasing very much. So before, with the filter, for the physical clogging, this decreased much more, yes. And, for the physical clogging, this decreased much less. And for the biological clogging, it decreases much more. And yes, now I compared them to the 2 setups in total. For this, I just said I have a 100% of hydraulic conductivity in the beginning, and now I just take a look at the percentages for the smallest one. So 20% of hydraulic conductivity, how do the other wells look like? 10% of hydraulic conductivity, how do the other 2 look like? And the same for the 5%, 2010 and 5. I had this small shift here. This is probably an artifact due to gas entrapment. However, you see that for the biological and physical clogging at the diameter, this effect is much stronger for the biological clogging than for the physical clogging at this biggest well that was also equipped with a filter gravel. For the diameter itself, it looks quite similar. But due to this, I also took a look at the gravel pack and the gravel aquifer, and there you see physical clogging is not affecting the gravel aquifer very much, and for the gravel pack, the gravel aquifer is not affected at all, and for the gravel pack, it's affected slightly, whereas biological clogging really decreases everything much more. So this led me to the conclusion that a gravel pack is actually very suitable if you expect physical clogging, But if you expect biological clogging only, it will help you to delay it a little bit, but not as much as for physical clogging. And those are also the conclusions. So gravel pack delays physical clogging significantly, biological clogging only in the beginning, and with time, this effect of the gravel pack becomes much, much weaker. For the diameter, the effects were not really significant, but this could be due to my limitations that they are much smaller than usually in practice. So I couldn't really compare them with anything that I had in the field. The setup was only tested for a certain set of parameters. So let's say if I use another sediment or another screen, more nutrients, less nutrients, this might all differ much more. And finally, the long-term effects, they might differ from the observations that were made here. You saw that most of the time scale was very short. So biological clogging happened within 3 days, 4 days. And furthermore, it's not a field scale. So if anybody of you is planning to drill 24 wells in the future with different setups, just call me and I would very much like to clog them. So yeah, thank you very much for your attention.
Thanks very much, Fritz. That was a very informative overview of your research. So has anybody got any questions for Fritz?
Very interesting lecture. I think you neglect one parameter. I don't know if it's important or not. It's the velocity of the recharge water. Transition from laminar flow to turbulent, which is definitely affected by the diameter.
Yes.
But again, I don't know if it's important or not.
I was thinking about this too. So I tried to have a look at the Forchheimer correction also for Dupuy team. But there are a lot of parameters that I cannot really assess. That's why I decided to keep it as simple as possible and to say I'm assuming laminar flow here, even though it's probably not correct, as you say. Yes?
Thank you for an informative presentation. Really liked it. Building on top of that, it's not just turbulent flow with velocity, but it's also the clogging risk, particularly the physical clogging on the change from the aquifer to your gravel pack. So the chances for clogging increase with increasing flow rates. And another aspect, you've looked at infiltration. How would you think would the clogging risks appear if you would look at abstraction?
I was thinking about how it looks for drainage systems. So if you build drainage systems with smaller diameters, I assume that it's kind of similar because again, this interface area is actually this is where the reactions take place. And so the smaller it is, the more will physical clogging affect it, and this effect of the growth of microorganisms or even chemical clogging, like precipitation of iron oxides or anything similar, they might show similar effects here, but I haven't tried it.
You also mentioned linear, that you expected linear, but your experiments clearly show that it's not linear. Yeah?
Yes, but this is because we reversed it. So if you reverse it again, it shows linear flow. So this is an anti-proportional relationship now. Before it was proportional, time to increase in resistance.
Okay. Peter?
Yeah, amazingly simple experiments which show a lot of things, which is very interesting indeed. But how did you fill up your columns? Can that have an impact? The way you filled up the sand, the way you filled up the gravel, is it representative for what we find in aquifers?
So actually, wait a second. I show the big one. So I actually just consolidated them in vertical direction. So I filled it 5 centimeters each layer, consolidated them, filled another 5 centimeters. So this is what I would expect for natural deposits most of the time. So vertical compaction. For sure, I cannot really say this is a homogeneous sediment that was sieved before. I cannot really say that in the nature it looks like this. And in addition to this, I forgot to mention that I only check confined conditions. to see this increase and to keep the filter area always the same. For unconfined conditions, this might change because then the filter area again always changes a little bit.
And the gravel pack, because normally you would throw it in vertically, you just dump it in the borehole. How did you construct that?
I constructed my own borehole of 13 centimeters. So I built up the sediment outside. I had a smaller pipe inside from where I filled the gravel, and then I pulled it out like a real drilling operator, but it's on a smaller scale.
Okay, thank you.
One last question up the back.
Thank you very much for your presentation. I would just like to ask you a question because I did not understand why. When you compare biological and physical clogging, you show the data, as if you can show it, please.
Mm-hmm.
Yeah, there you go. We have the data that one arrives until 6 hours and the other one is until 84. Do you have any reason because of that? I mean, I understand one process and the other are different and the speed is different as well. But which was the reason to show this data until this moment?
Yeah, I should have mentioned that the biological clogging experiments, they took much, much more time because at first you need this initiation phase, while physical clogging is a much simpler process. It just immediately starts and then it increases rapidly. So I decided to have those more or less 4 days, little less than 4 days, because this is what I could assure. It was quite difficult to keep all the conditions always the same with this simple experiment. But this is where I actually can assure that the conditions stayed the same. And I think somehow it's comparable because I always say I oriented on the lowest hydraulic conductivity. So I always said when I reach 20% with the lowest one, I take a look how the other one changed, and the same for this. So this might change as soon as you change some parameter, as I said, in the limitations. But yeah, this is as far as I could get.
Okay, so you fixed your own criteria on a certain level of...
Yes.
Okay. I understand. Thank you.
As the moderator, I might sneak in one last question. What did you inoculate the bores with? What microbes were you actually using to test the microbiological clogging?
I used what was inside the sediment. So I just added glucose and some fertilizer.
Right.
So I know the amounts of nutrients that I had. I fixed this, but the microbes growing were mainly in the sediment present already.
Yeah, so you just used what was present in the sediment. You didn't sterilize and then inoculate.
No.
Okay.
But I used the same sediment always, and it was a little older then, but I assumed that they are always, that it's the same microbiology.
Yeah.
Oh.
Okay, thanks very much, Fritz. Any other questions? I'm sure Fritz will take it.